Right topic, gas laws. Right topic, gas laws. Okay, the chemistry ones may have some experience in this section. The IT ones, maybe you have forgotten. You have done a bit of this in O level. But I'll start from simple and we keep on moving forward. Right. Now, under gas laws, we'll be talking about gases. You can see if you take the states of matter, you have solids, liquids, as well as what? Gases. Solid, liquid, gases. And if you take gases, their intermolecular forces of attraction are very, very what? Strong or weak? Weak. Because they are weak only what? They can freely what? Move. Is it clear? Freely move. And if you take this space, gas or the air is filled this complete volume. Every single place in this particular room or this hall is filled with what? Gas molecule. So the complete shape or the complete volume of this particular hall has what? Air. If you take a container, the volume of the container and the volume of air both are what? Same. Is it clear? So here if you look at it, gases have weak intermolecular forces. Gases have weak intermolecular forces. Clear? Now, in our syllabus, we speak about a special type of gas. What do you call those gases? Ideal gases. Clear? Ideal gases. So we are learning a model. We talk about what? Ideal gases. Now the word ideal is also there. No? It's clear. Ideal gases actually do not exist. Clear? Ideal gases actually do not exist. But what we do is, we study about ideal gases and any variations in the ideal gas, they have separate set of equations. For example, the chemistry ones might have learned something called Van der Waals equation. Now, Van der Waals equations can be applied for what? Real gases. But we will not go so far. We will stick only with what? Ideal gases. Right. Now, ideal gases are based on certain assumptions. Yeah. So we are learning about the ideal gas model. And these ideal gases are based on certain what? Assumptions. Look at this carefully. The first assumption is all gas particles are considered as point masses. All gas particles are considered as what? Point masses. Next, all collisions between gas particles and the walls of the container are perfectly what? Elastic. So you have perfect what? Perfect elastic collision. Perfect elastic collision. Third one. The intermolecular forces of attraction or repulsion between ideal gas molecules is going to be what? Zero. So no intermolecular forces, no intermolecular forces of attraction or repulsion. Of attraction or repulsion will exist between the gas molecules. There will exist between the gas molecules. Next one. The time of collision between two gas molecules, again, that means the gas molecules are colliding, no? Collide one more. All are in random motion. What motion? Random motion. There is no fixed path. Next assumption is, since the gas particles are colliding randomly, if two gas particles, let's say A and B collide, there you have infinite number of gas molecules. We have a gas molecule called A, we have a gas molecule called B. A and B collide. For A and B to collide back again, the time taken will be very, very large. We don't know when A and B will collide back again. There. So time of collision for A and B, or the time took for A and B to collide again, is what? Very large compared to the time taken for the collision between A and B. So A and B colliding, let's say millisecond. But for A and B to collide back again, the time taken is very, very large. There. So for two molecules, time taken to collide again is very large. Time taken to collide back again is very, very large. I have seen in chemistry they have put as an assumption the kinetic energy of an ideal gas is directly proportional to the absolute temperature. You can't write that as an assumption because you will prove it under ideal gas theory. Chemistry fellows who do Boltzmann curve, you are proving no later kinetic energy is equal to 3 over 2 kT or 3 over 2 nRT. How can that be assumption? Don't write the assumptions you write in chemistry and physics. Huh? Some assumptions you write in chemistry are not assumptions in physics. Be very, very careful. Some assumptions you write in physics, clear, are facts. We prove and do it later. In chemistry, maybe you can write according to your marking schemes. That's a different story. Don't mix both. They are two different things. You'll realize we are doing two different things the moment you what? Start solving problems. We don't solve easy problems like you solve in chemistry. Is it clear? Right. So mainly these are your 5 assumptions. What are your 5 assumptions? All the gas particles are considered to be what? Point mass. All collisions between gas particles and the walls of the conductor or the container are what? Perfectly elastic collision. No intermolecular forces of attraction or repulsion between the gas molecules. There. Now remember, this is very important. No intermolecular force of attraction or repulsion means potential energy change, the change delta, potential energy change will be 0. So intermolecular forces of attraction are not there means potential energy is also not there. Understood? Right. Or in random motion, I think random motion. And the time taken for 2 gas particles to collide back again, let's say 2 gas particles collide, for them to collide back again, the time taken is very, very large. Is it clear? So the time taken for collision between them is negligibly small. Clear? Right. Let's write this. Gas laws. Let's write. Gases have weak intermolecular forces of attraction between them. Gases have weak intermolecular forces of attraction or repulsion between them. Or repulsion between them. In our study, we will only consider ideal gases. We will only consider ideal gases. In our study, we will only consider ideal gases. We will only consider ideal gases. Next line, right? Ideal gases are based on the following assumptions. Ideal gases are based on the following assumptions. Based on the following assumptions. Let's write point number 1. That's right. The gas consists of very small particles. The gas contains very small particles where all the particles have the same mass. Where all the particles have the same mass, and they can be considered as point masses. And they can be considered as point masses. Next assumption. Second one. All the gas particles are in random rapid motion. All gas particles are in random rapid motion. All gas particles are in random rapid motion. Next one. All collisions between gas particles, all collisions between gas particles, all collisions between gas particles and the walls of the container are perfectly elastic. And the walls of the container are perfectly elastic. Walls of the container are perfectly elastic. Next point. There is no intermolecular forces of attraction or repulsion. There is no intermolecular forces of attraction or repulsion. There is no intermolecular forces of attraction or repulsion between the gas particles. Between the gas particles. This means the change in potential energy will be zero. The change in potential energy will be zero. Next point. The time taken for two gas particles to collide back again. The time taken for two gas particles to collide back again. For two gas particles to collide back again is negligibly small. Is negligibly small. Sorry. Is at the word negligibly. The time taken for two gas particles to collide back again is very large. Is very large. The time taken for two gas particles to collide back again is very large compared to the time taken between collisions. Compared to the time taken between collisions. Compared to the time taken between collisions. Okay, no? So our assumptions are done, right? Now we'll move forward. When it comes to gases, we always consider three quantities: pressure, volume, and what? Temperature. Every variation will take place between three quantities. What is it? So if you have a gas, remember it's pressure, volume, and always what? Temperature. Now, temperature we measure not using Celsius, we measure using what? Kelvin. So, for example, if somebody says 27 Celsius, when you substitute, it actually should be how much? 300 Kelvin. Always we substitute in Kelvin. Yeah. So, 127 Celsius means how much? 400 Kelvin. All measurements are going to be what? In Kelvin. Volume, generally we consider meter cube. Normally volume of container equals volume of gas. Equals volume of what? Gas. So volume of the container and volume of the gas both are what? Same. Sometimes they won't specially say the volume of the gas is this. They'll give you the volume of the container. Then you should know volume of container and volume of gas both are what? Same. There. Now pressure occurs because of these intermolecular forces when they collide. Or when they collide, now look at this. A gas particle M coming and colliding and rebounding. Coming, colliding, rebounding. When they collide and rebound, there is going to be a change in momentum, no? That means there will be a force. Force divided by this area is going to give you what? Pressure. 2004 A-level essay question, which you have done under collisions in your law of conservation of linear momentum tube. There you find the pressure. I think the answer is 40,000 Pascal or something. There, gas particles collide, they rebound. There is a momentum change. Momentum change divided by time is going to be what? Force. Force for one gas particle multiplied by number of gas particles will give you total force. Total force divided by the area is going to give you what? Pressure. That is how the pressure inside a container is measured. There. But generally what happens is, that's the mathematical calculation. Normally inside a container, you have something called a gauge meter, pressure gauge. Pressure gauge. Pressure gauge will always measure what? Gauge pressure. What is gauge pressure? Gauge pressure is the total pressure without atmospheric pressure. I hope you remember this one, the fluids. Absolute pressure is atmospheric pressure plus gauge pressure. This gauge pressure only is what? Normally H rho G. H rho G is directly measured using a pressure gauge. Understood? So whoever was thinking, how do they measure pressure inside? They use a pressure gauge. Pressure gauge measures gauge pressure. Volume of the container equals volume of the gas. And all temperatures are measured using what? Kelvin. You know? That's right. That's right. Under gases, we will consider three main quantities. Under gases, we will consider three main quantities. They are first one, pressure. First one, pressure. That's right. Pressure is measured using a pressure gauge. Pressure is measured using a pressure gauge. Pressure is measured using a pressure gauge. This measures the gauge pressure. This measures the gauge pressure. Inside brackets, write H rho G. So H rho G is called gauge pressure. you want, write the equation again. Some of you all have forgotten. Absolute pressure equals atmospheric pressure plus gauge pressure. Quickly write. Absolute pressure equals atmospheric pressure. Now we have for median or PATM plus gauge pressure. Normally, if they draw a diagram and they give you a gauge, pressure gauge, it always measured what? Gauge pressure. The gauge pressure. Right. Next one. Volume. Next one is volume. So what can you say? Volume of the gas equals volume of the container. Right now. Volume of the gas equals volume of the container. Volume of the gas equals volume of the container. Right now. Third one, absolute temperature. Third one, absolute temperature. Third one, absolute temperature. I put some examples now. 27 Celsius is 300 Kelvin. 127 Celsius is 400 Kelvin. All of you all know this under thermometry. We have done this. So how do you convert Celsius to Kelvin? At 273.15 for real. But in physics, we normally say 273. Okay. Right. Okay, no? So now I'm going from simple to complex. Huh? Even the IT people, pressure, volume, temperature, then the assumptions. But we are only not sticking with ideal gases. Yeah. We are just sticking with ideal gases. Right. Now, mainly we have three laws. You call them gas laws. Every single calculation you do can be connected to one of these three laws. Or many states you have two or more equations. And later we'll build something called the ideal gas equation. Yeah. Now when we build the ideal gas equation, you will realize we are learning more than chemistry. The chemistry people will know that. Is it clear? Chemistry all have gone up to a certain level and you all just ignore it. But we are just moving more than that. Yeah. So under gas laws, we first consider Boyle's law. Boyle's law. Now, what is Boyle's law? Remember, all these gas laws are valid for what systems? Closed system. They are valid for what systems? Closed system. That means no mass is coming in, no mass is going out. Clear? No mass is coming in, no mass is going out. Whatever the mass inside is inside. That's it. So normally we say fixed mass of gas. Fixed mass of gas means no gas is coming in, no gas is going out. You know? So for a fixed mass of gas, I'll draw and show you. So this is a container. Nothing is coming in, nothing is going out. For a fixed mass of gas at constant temperature, when I put a box there, it means constant. Mass is constant, temperature constant. Pressure is inversely proportional to volume. Pressure is inversely proportional to volume. For a fixed mass of gas at constant temperature, pressure is inversely proportional to volume. That means when volume increases, pressure reduces. Volume reduces, pressure will what? Increase. There. Now you can make this equation. P proportional to 1 over V. P is equal to K times 1 over V. Cross multiply this, we can say PV equals K. PV equals K. They might ask you, what does this K depend on? K will depend on whatever is constant. It will depend on the mass. It will depend on what? Temperature. That means what do you learn? When the mass and temperature change, K will also what? K. Some things that the chemistry people don't know. They think PV something, quickly you can apply and go. No, no, no. We can apply the relationship only if the same mass is there, same temperature is there. And the most important thing, same gas should also be there. Fixed mass of gas at constant temperature, pressure inversely proportional to volume. Okay. Now look at this. I have a piston cylinder arrangement. Mass of gas is fixed. Here pressure P1, volume V1. After some time, piston moves up somewhere here. Same mass, no? Mass won't change. No mass has come, no mass has gone. Now pressure is P2, volume is T2. Temperature here is same, T. Now be very careful when you write this. Same mass, same temperature, P1, V1 equals, let's say, K1. I can write here now. P2, V2 equals what? K1 itself. Why? Same mass, same temperature. Now you can see both the K1s are equal. Therefore, we can say P1, V1 equals P2, V2. There you go how you apply Boyle's law for two systems where you have the same mass of gas, same temperature. Technically, the same mass only is undergoing this process. You call this what? A thermodynamic process. Later, it's important. Thermodynamic process. So you are moving from one thermo situation to another thermo situation. Same mass of gas at the same temperature. That is why the K values are what? Clear, no? Right. Let's try this. Boyle's law. Right, main topic gas laws. Under that, the first one, Boyle's law. First one, Boyle's law. That's right. For a fixed mass of gas, at constant temperature, pressure is inversely proportional to the volume. Pressure is inversely proportional to the volume. Pressure is inversely proportional to the volume. Quickly draw this. Fixed mass of gas, constant temperature. Pressure is inversely proportional to volume. So volume increases, pressure reduces. Volume reduces, pressure will what? Increase. There you go. Right, no? So this is your main law. Then you can write for these two thermodynamic processes. Let's write. For a thermodynamic process, for a thermodynamic process, we can apply Boyle's law as indicated below. For a thermodynamic process, we can apply Boyle's law as indicated below. We can apply Boyle's law as indicated below. Quickly apply. This complete theory about 1 hour, then we can solve problem. Right now? Okay. So same mass of gas undergoing a thermodynamic process, becomes bigger, whatever. Same temperature. P1 V1 is K1, P2 V2 is K1. Both the Ks are same, so P1 V1 equal P2 V2. Clear? No? Right. Now look at this. Pressure equal K times 1 over V. So we can plot a graph between volume and pressure. The curve is very simple. It's a curve like this. Exponential curve. Volume increases, pressure will reduce. Volume reduces, pressure will what? Increase. Exponential curve. But something you might not know. These curves are called, along this curve, the temperature is constant. Along this curve, what is constant? Temperature is constant. Right? No? Why? Full system temperature is what? Same. If I look at this very carefully, look. Pressure P1, sorry. Pressure P1, volume is V1. Pressure P2, volume is what? P2. Okay. So we are applying this along this line. Here also temperature same, here also temperature same. Along this line, everywhere temperature is what? Same. Now these points you all don't know in chemistry. Along this line, everywhere temperature same. So we call this line isothermal line. What do you call it? Isothermal line. Isothermal means constant temperature line. Clear? Next. Different temperatures will have different isothermal line. Different temperatures will have different isothermal line. We can draw like this. Different isothermal. Here temperature T1, here temperature T2, here temperature T3, here temperature T4. How do you know which temperature is smaller or bigger? Bigger temperatures will move away from the origin. T4 is larger than T3, larger than T2, larger than T1. Smaller temperatures are closer to the origin. Higher temperatures are what? Away from the origin. What is important? Along this line everywhere, temperature is what? What do you call it? Isothermal line. Yeah. Draw. That's right. For Boyle's law, we can plot the following graphs. For Boyle's law, we can plot the following graph. For Boyle's law, we can plot the following graph. Keep writing. When we represent Boyle's law, the temperature along any point, the temperature along any point along the curve will be constant. Along the curve will be constant. We call this a isothermal line. We call this a isothermal line. We call this a isothermal line. Work. Draw. So these are isothermal lines, but they are at different temperatures. Huh? The outer being higher temperature, inner being smaller temperature. Right? Okay. Enough, no? Clear, no? Okay. Some more graphs. P equals K times 1 over V. Graph is of the form Y is equal to mx. So if I plot a graph 1 over V versus pressure, it's a straight line going through the origin. Now why I put some dot lines here? 1 over V will be 0 only when V goes to what? Infinity. So infinite volume is not defined like a thing. No? So we show anyway it goes to the origin like this. Right. Next, what else? They'll ask you to draw PV versus volume, and they might ask you to draw PV versus pressure. But all of you all know P is going to be a constant. So even if volume increases, PV constant. What's going to happen? When volume is increasing, pressure will what? Reduce. PV magnitude will always be what? Same. So PV is going to be same. Same here. Pressure might increase, volume will reduce, PV is going to be constant. Sometimes they can represent using a log graph as well. How is that? PV is equal to K, no? Take log from both sides. Multiplication means addition. From this we have log P minus log V plus log K. Graph is of the form Y is equal to minus X plus C. That means here log V, log P, here represented Y equal minus X plus C. Graph is like this. Plus C is your intercept, that's your log K. Clear, no? Okay. Now these things are new for you. Draw. Always when you're drawing graphs, don't forget to put the origin. Important. Okay, no? Drop it quickly. Right, no? Quickly draw. Okay, right. Then the next law is called Charles' law. Boyle's law is there. Charles' law is there. Now, what did Charles tell you? For a fixed mass of gas at constant pressure, earlier what? Fixed mass of gas at constant what? Temperature. Here, fixed mass of gas at constant pressure, volume is directly proportional to the absolute temperature. Volume, absolute temperature means Kelvin temperature. That means when temperature increases, volume will increase. Temperature reduces, volume will what? Reduce. You can make this equation V equals KT. K depends on two things. What does K depend on? K depends on mass and pressure. Now look at this thermodynamic process. Piston cylinder arrangement. You know how they will say constant pressure? Piston is free to move. I'm not pulling the piston. Imagine a syringe. You press the syringe is just going up without your help. Or just going down without your help. If the piston is free to move, we call it what? Constant pressure process. Clear? So piston is free to move. That's another way to say pressure is constant. When somebody says piston is free to move, don't forget pressure is going to be what? Constant. So here fixed mass of gas, constant pressure, volume is V1, temperature T1. Now thermodynamic process will take place. Thermodynamic process will take place. Thermodynamic process. Now the piston has gone up a bit. Same mass of gas. Same pressure. Volume, temperature. Now I can write here. Look at this carefully. V1 equals K1 times T1. V2 equals what? K1 times T2. Why? Same mass, same pressure. No? Now I can divide one from the other. V1 over V2, K1 T1, K1 T2, K1 K1 cancel off. Therefore you can say V1 over V2 is equal to T1 over T2. From this you can modify this a bit and take. Or best way is I'll represent it like this. Okay, look. V1 equals K1 T1. V1 over T1 equals K1. Easy, no? This you can write V2 is equal to K1 T2. V2 over T2 is K1. Equation 2. What can you say about 1 and 2? 1 and 2 are equal. Therefore, you can say V1 over T1 equals V2 over T2. There you go. What do you call this? Charles law. That's right. Charles law. For a fixed mass of gas, for a fixed mass of gas at constant pressure, fixed mass of gas at constant pressure, volume is directly proportional to the absolute temperature. Volume is directly proportional to the absolute temperature. Volume is directly proportional to the absolute temperature. Work. Right? Okay, look. Right? Okay. Now, how do I represent this in a PV graph? None of you all in chemistry know how to represent this in a PV graph. How do I represent Charles law in a PV graph? What do you learn? PV graph. Charles law, pressure is constant. Initial volume V1, pressure is P. Final volume V2, pressure is same, P. Okay. So actually, this is how you represent Charles law in a PV graph. You might say, sir, how do you know this is the one? Can you remember? PV graph, we drew isothermal line. PV graph, we drew isothermal line. This isothermal line temperature is T1. This isothermal line temperature is T2. Pressure is P. So what do you have here? Volume V1, temperature T1. Volume V2, temperature what? T2. What do you call this line? Isobaric line. What line? Isobaric line. Constant pressure line. Clear? Now I'm giving you a broader view, not a narrow view like in chemistry. PV curve. Now we think about isothermal lines and where to draw this in an isothermal line curve. There. So here you have isothermal line. We learned, no? There. Larger volume, larger temperature, smaller volume, smaller temperature, right? Smaller temperatures are going from down, larger temperatures are going from top. There. And here pressure P is same where it cuts the line here. V1, T1, V2 what? T2. Clear? So this point you can write V1, T1. This point you can write V2, T2. So along this line you can say V1 over T1 equals what? V2 over T2. Is it clear? Okay? New, because you are representing this in what curve? PV curve. Understood? That's right. We can represent Charles' law. We can represent Charles' law in a PV curve as indicated below. In a PV curve as indicated below, along an isobaric line. Along an isobaric line. Along an isobaric line. Draw. Right, no? And now we can draw volume temperature curve. V equals kT. Y equal mx. So here temperature in Kelvin, volume. But remember 0 Kelvin has never been reached. Since 0 Kelvin has never been reached, dotted lines goes through the origin. Y equal mx form. You can modify this a bit further. V equals kT. Kelvin temperature I can write in Celsius temperature like this. V equals k theta plus k times 273. Graph is of the form y is equal to mx plus c. So if I plot If I plot, I will do it like this. You know. If I plot the graph, temperature in Celsius, volume here, negative side is also there. 0, 0 is y equal mx plus c. And the best part, extend it. Here, k times 273. If you extend this, because the gradient is k, it will cut somewhere here. Now, all of you all know the gradient of the graph is k. What do you mean by gradient of the graph? Angle made with the horizontal, no? Tan angle made with the horizontal, right? Graph work. Gradient of the graph here, gradient of the graph. So gradient of the graph here is, gradient is tan alpha. What is your gradient? K. Tan alpha is opposite to adjacent. K times 273 divided by, this distance is a negative value. Negative value I'll just put as, let's say, negative y. These in the x-axis, no? Negative x. This distance will be a negative value. K cancel off. X equals minus 273. It will cut here at minus 273 Celsius. Okay, no? Now this you are familiar with your chemistry knowledge. If you plot the graph volume temperature Celsius, this straight line will cut at minus 273. That is called absolute zero. If it's Kelvin temperature, it's going through the origin. This is something that you don't know. Today only you know this. PV curve, if I draw this, it will be along an isobaric line between two isothermal curves. Higher temperature curve, lower temperature curve. Here, if you want, you can mark T2 is larger than. Clear, no? That's right. We can plot a graph between volume and temperature. We can plot a graph between volume and temperature as indicated below. We can plot a graph between volume and temperature as indicated below. Draw. Quickly work. Okay, no? Right? And the final law, pressure law. There, pressure law. So Boyle's law, what happened? Mass is constant, temperature constant. Charles law, what happened? Mass is constant, pressure is constant. Pressure law, what will happen? Mass is constant, volume is constant. So pressure and temperature will change. So pressure, volume change, we know, Boyle's law. Volume, temperature change, we know, Charles law. The only thing that should happen is what? Pressure and temperature should change. There. So pressure law, that gives you this idea. For a fixed mass of gas at constant volume, pressure is directly proportional to the absolute temperature. That means when temperature increases, pressure increases. Temperature reduces, pressure will what? Reduce. There. From this, what can we say? Look at this carefully and tell. Huh? Look at this carefully. Pressure proportional to absolute temperature, pressure is equal to K times T, where K depends on mass and volume. There. K depends on mass and volume. So here, if I take two thermodynamic systems, same volume, fixed mass of gas, same volume, pressure here P1, temperature T1. Thermodynamic, volume is constant. Volume constant. Volume constant, no change in volume. Piston cylinder arrangement. Mass is same, volume is same. Pressure P2, temperature T2. What can you say? Pressure is equal to K times K1 times T1. P1 over T1 equals K1. Same mass, same volume, same mass, same volume. P2 equals K1 T2. P2 over T2 equals K1. These two K1, K1 are equal, therefore you can say P1 over T1 equals P2 over T2. There you go. Yeah, there you go. So earlier V1 over T1 equals V2 over T2. Here P1 over T1 equals P2 over T2. Okay, no? Right. That's right. Pressure law. For a fixed mass of gas at constant volume, for a fixed mass of gas at constant volume, for a fixed mass of gas at constant volume, pressure is directly proportional to the absolute temperature. Pressure is directly proportional to the absolute temperature. Pressure is directly proportional to the absolute temperature. Work करो quickly. Right? So these are thermodynamic process. Same container, mass and volume same, pressure and temperature will change. Clear? Now, how do I represent this in a graph? We'll first start with the PV graph. PV graph, how to represent? Constant volume. Temperatures are different. So two isothermal lines. One will be T1, one will be T2. Constant volume means V is same. Constant volume means a line like this, no? Right. Pressure, volume. So here, pressure P1, temperature T1. Pressure P2, temperature T2. You know? Your process is from here to here. Normally we'll put an arrow, but for now I'll just show the line. This is called constant volume line or isochloric line. Isochloric Chloric means water or volume. Isochloric line. Isochloric. And what do you call this? Isobaric line. Constant volume line. And this is called isothermal line. These are called isothermal. Okay, no? Isothermal, isochloric, isobaric. Okay, no? So that's your process in a PV curve. Pressure equals K times T. Y is equal to mx absolute temperature. Absolute zero has never been reached, but it is a line going through the origin. We can also convert this to Celsius. How is it? P equals K times theta plus 273. Open brackets, K theta plus K times 273. Graph is of the form y equal to mx plus c. Y is equal to mx plus c. So now if I draw the curve, temperature in Celsius, pressure, your curve is anyway y equal mx plus c. Y-intercept is k times 273. We want to find out the temperature there, so alpha is the gradient. Tan alpha equals gradient. Gradient of the graph is k. What is tan alpha? Opposite. Opposite is k times 273. Adjacent is negative side of x. Negative x-axis is minus x. K cancel off. X equal minus 273. It will cut here at minus 273 Celsius. You know? That's right. We can plot the following graph. We can plot the following graphs for the pressure law as indicated below. For the pressure law as indicated below. For the pressure law as indicated below. Quickly work. Right? Okay. Boyle's law, Charles law, pressure law done. Final combined gas law. Draw this into three states quickly. Draw will. Thermodynamic states. Draw. Combined gas law. So P1 dash. No, we put P1 dash. V2, V3. The middle one is like an intermediate state. Intermediate state. Combined gas law, combined gas equation is the word. Right. Look at this carefully, Willow. Fixed mass of gas undergoes thermodynamic process means no gas is coming in, no gas is going out. Mass is same. No gas is coming in, no gas is going out. Mass is same. There you go. Now here you can see mass is same, temperature same. So you can apply whose law? Boyle's law. So between the first and the second you can say P1 V1 equals P1 dash V1 dash. Okay, no? Yeah. P1 dash V1 dash. This is your equation. If you want, you can say equation number 1. Looking at these two, what can you say? Fixed mass of gas, pressure is same. Fixed mass of gas, pressure is same. We can apply Charles' law. V1 dash over T1, V2 over T2. Correct, no? Clear, no? Right. Equation number 2. Quickly write it. So first container, second container, you can apply Boyle's law. You can apply Boyle's law. Second container, third container, you can apply Charles' law. You can apply Charles' law. Right. Clear? Okay. Now what? From the first equation, V1 dash the subject. V1 dash is going to be what? V1 dash is going to be P1 V1 over P1 dash. P1 V1 over P1 dash. Now we can take this and substitute to equation number 2. We can take this and substitute to equation number 2. Write it carefully. P1 V1, P1 dash, V1 dash. Between these two you can write Charles' law. From the first equation you can make V1 dash the subject, P1 V1 over P1 dash. Let's substitute there. Or shall I simplify it even further because these two will come nicely. Make this value P2 at once. Finish. Make this P2. Then write. Make that P2 value. P1 dash, make it P2. Same, no? So here also you can put P2. Easier, no? Because some of you all don't like dash values. No? So we can make this also like this. Put P2. P1 V1 equal P2 V1 dash. Make V1 dash the subject, P1 V1 over P2. These two, of course, no issue. P1 dash over T1, V2 over T2. Just change these two to P2, P2. I just put P1 dash, P1 dash. No need dash values, we'll put P2, P2. Easy, no? Right. Now take equation 3, substitute to equation 2. Do it. From 3, substitute to 2. Quickly do it. Wherever there is V1 dash, substitute this. P1 V1 divided by P2 over T1, V2 T2. Carefully rearrange. P1 V1 over T1 P2, V2 T2. Put the P there now. P1 V1 over T1 equals P2 V2 over T2. Interesting, no? Can you remember PV constant? That means P1 V1 equals P2 V2. Okay. V1 over T1 equals V2 over T2. That means what? V over T is constant. P1 over T1 equals P2 over T2. That means what? P over T is what? Constant. P1 V1 over T1 equals P2 V2 over T2. What can you say? PV over T is going to be what? Constant K. And what does that constant K depend on? In all these three states, what is same? What is same? Mass is same. Depends on the mass. Depends on the mass. PV over T is constant. K depends on mass. K depends on what? Right? This is the combined gas equation or equation of state. Some people call this equation of state as well. Equation of state as well. Right? Okay. Okay, now? Right. Now look. Finish writing. Now look. Huh? So this is your equation of state. PV over T is K. Constant K depends on the mass. Listen carefully. He is now going beyond chemistry. Huh? I want to ask you now, for the chemistry students, how did you all get PV equal nRT? How? PV over T is K, no? Huh? I'll tell you the next step. Next step, you all wrote K is equal to NR and wrote this. That's it. You all don't know the actual process. Look at this carefully. Constant K can be defined in three different ways. Look at this carefully. Understood? Constant per mole. Constant per mole. Constant K per mole for the IT students. Mole symbolically represented as N. N represents number of moles. Don't worry much. Number of moles is mass of gas divided by molar mass of gas. Molar mass normally in the periodic table or whatever they'll give you. For example, let's say the molar mass of hydrogen atom is what? 1 gram per mole. Hydrogen gas H2 is what? 2 gram. The molar mass of oxygen atom is how much? 16. O2 is how much? 32. Like that. So normally they'll give that, so don't worry. So mass of the gas, that's simple M, over molar mass is capital M. That will give you number of moles. Constant per mole is defined as universal gas constant. R is defined as what? Universal gas constant. Value 8 point what? 314 joule per mole per what? Kelvin. Normally in our calculation, we just take, I think in chemistry, or take the whole thing. We take 8.3 or 8.31 depending on what they give. There. Generally 8.3 is more than enough for us. Clear? Right. The constant per mole is defined as universal gas constant. Cross multiply. K is equal to NR. Therefore, you can say PV over T is equal to NR. Therefore, we have PV equals nRT. This is one equation which we can use. Clear? That's right. The universal gas constant capital R, the universal gas constant capital R, the universal gas constant capital R is defined as constant K per mole. Constant K per mole of the gas. Constant K per mole of the gas. Clear? Work quickly. the the chemistry ones, of course, know this, but the IT ones, you all study it. Huh? Mass of gas, molar mass of gas. You might need a mass of gas, let's say, is in kilograms. Molar mass will be kilograms per mole. Huh? That's the unit. Kilograms per mole. Okay, no? Kilograms per mole. Right? Okay. Now, chemistry people stop here. PV equal in RT. But in physics, we don't stop there. We have to move forward. There are two more equations we need to know. There. Two more equations we need to know. I hope you all have finished this. Huh? Right. The next equation is, look at this carefully. PV over T is constant K. Listen carefully. Constant per mass of gas. M is mass of gas. Remember the symbols, please. M is mass of gas. I have defined. Capital M is molar mass of gas. Look at this. Constant per mass is R dash. R dash is gas constant. R dash is gas constant. Here you can write joule per kilogram per Kelvin. You might say, sir, what is gas constant? From gas to gas, the gas constant will what? Change. Universal gas constant, word is there, universal. Any gas, same. Gas constant will change from gas to gas. Cross multiply here. K is equal to MR dash. Therefore, we have PV over T is equal to MR dash. Therefore, we have PV is equal to MR dash into T. Can you apply this for any gas? Yes. But for that particular gas, you should know the gas constant. Nitrogen will have a separate gas constant. Oxygen will have a separate gas constant. Helium will have a separate gas constant. Okay, no? Right now. Second relationship. That's right. Constant per mass. Constant per mass. Constant K per mass is defined as constant K per mass is defined as the gas constant. The gas constant. The gas constant. For different gases, we will have different gas constant. For different gases, we will have different gas constant. Quickly write down. Okay. Right. Look at this now. PV over T is K. Yeah. We can define constant per number of molecules. Capital N is number of molecules. Huh? Constant per molecule is Boltzmann constant. Boltzmann constant, you write a K with a bow at the back. You have seen frocks, girls with the bows. Like that, you put a K at the back. Yeah. So here it will come like this, then here like that. Boltzmann constant. That's Boltzmann constant. So N is number of molecule. Number of molecule. Boltzmann constant. Boltzmann constant. Now you can rewrite this. Constant is number of molecules into Boltzmann constant. Therefore, you can write PV over T is equal to N times K. From this, you have another equation. PV equals NKT. Now you can see, not like in chemistry. In physics, when we solve gas laws, we have a lot of what flexibility. We just don't know one equation. We have how many equations? 3 equations equal to PV. If they are given molecules, we can work in molecule. If they are given mass, we can work in what? Mass. If they are given moles, we can work in what? Mole. Whichever way, we can what? Work and get the required relationship. Okay, no? Write down. Constant K per molecule. Constant K per molecule. Constant K per molecule is defined as constant K per molecule is defined as Boltzmann constant. Boltzmann constant. Work. Even the chemistry people learn gas laws correctly in physics. Then later when you do physical chemistry, which is where gas laws are very important, you won't have an issue. If you just know whatever you learn in chemistry only and go, you have no flexibility to think. You'll have a problem. Because they always tell you to think in terms of what? Number of moles. But you can think in terms of number of molecules as well. That is much more easier in the approach. Right? Okay. Now you have 3 relationships for K. K is equal to MR dash. K is equal to N times Boltzmann. K is equal to simple NR. There. K is equal to simple NR here. So I'll circle this a bit. I'll circle this a bit. I'll circle this a bit. All we are talking about is what? The same K. We are talking about the same K. Look at this carefully now. Huh? K is equal to NR. K is equal to MR dash. K is equal to N times Boltzmann constant. Now look at this. I will take these two separately. NR equals MR dash. What is this now? Number of moles. IT people, what is number of moles? Mass of gas divided by molar mass of gas. Mass of gas divided by molar mass. MR dash. What can you say about the M here? Both are what? Same, mass and mass. Now we can say gas law or gas constant is universal gas constant divided by molar mass. That means if I want the gas constant of hydrogen, H2, universal gas constant divided by molar mass of what? Hydrogen. If I need the gas constant of oxygen, universal gas constant divided by molar mass of what? Oxygen. Understood? From there I can get the gas constant. Look at this now. This one and that one. NR, NK, Boltzmann. How do I find Boltzmann? NR over N. I can slightly rearrange this. Number of molecules per mole. Number of molecules per mole. There was a person called Avogadro. Avogadro said, every mole will have what? A fixed number of molecules. 6 point something 10 to the power 23. Exact value you ask the chemistry student, they might know. Is it clear? They know to memorize and remember those. Clear? Number of molecules per mole is defined as Avogadro's what? Constant. In physics, the symbol we use is capital Na, but the fellows in chemistry will use what? L. Clear? Don't worry, you can use L. There is no problem. But whatever you use, you define it. Na, number of molecules per mole. So K here I can write universal gas constant divided by Avogadro's number. That is called Boltzmann constant. If you want to find Boltzmann constant, universal gas constant divided by Avogadro number. 8.314 divided by what? 6.022 or 23. 22 10 to the power 23. So if I 8.314 joule per mole per Kelvin divided by how much? 6.022 10 to the power 23 number of molecules per mole. Okay, no? Number of molecules. Avogadro constant is number of molecules per mole. If you divide this, you can get Boltzmann constant. Value for Boltzmann constant. So joule per Kelvin, it will come. To divide it, you will get a particular value. Clear, no? So here you have Boltzmann constant is universal gas constant divided by Avogadro number. Clear, no? Right now. I'll divide and tell you the value. 1.2 something. 1.38 10 to the power minus 23. Boltzmann constant. Boltzmann constant. There you go. Sorry, units are joule per Kelvin. Joule per Kelvin. No, Boltzmann won't vary with gas type, right? R is universal. Any gas, same, 8.314. For any gas, Avogadro constant also is what? Same. 6.022 10 to the power 23. So Boltzmann constant will also be a constant. So you all have learned in chemistry Maxwell-Boltzmann curve. Big name, small idea. You know? Today we'll finish this theory part. Then next week we can spend time solving problem. So just two more notes, small notes to give. Then we can have a break. Right? Okay, look. So remember these, huh? Clear? Right. Concentrate for 10 minutes. Let's say there is a container. There are n number of molecules. N number of molecules. Each molecule has a different speed, randomly traveling in all directions. Randomly traveling in all directions. That's for the nth particle. We can define mean squared velocity. Mean squared velocity. What do you mean by mean squared velocity? The symbol is c bar squared or c squared bar. Mean squared means, look at the board please, you are squaring all the velocities. You are squaring all the velocities. When you square all the velocities, direction won't be important. And you divide it by number of gas molecules. By now you should know capital N is number of molecules. The symbol name you should know. That will give you mean squared velocity. Remember this. Mean squared velocity is velocity squared. What are the units? M squared S minus 2. Does it give a velocity? No. It's giving square of the velocity. So we then define here number of molecules. Huh? N is number of molecules. Right. From here we define root mean squared velocity. Root mean squared velocity. Root mean squared velocity. Look at the symbol. T squared bar square root. That means this whole thing square root. C1 squared, C2 squared, C3 squared, C4 squared, Cn squared divided by number of molecules. So now you know how to find mean squared velocity. What's the unit here? The moment I take the square root, meters per second. Root mean squared velocity. Symbol for root mean squared is mean squared square root. That is root mean squared velocity. Some people put this also, RMS velocity. That also is what root mean squared velocity. RMS velocity. Okay, no? Let's say. Consider capital N number of gas molecules. Consider capital N number of gas molecules. Capital N number of gas molecules traveling with speeds C1, C2, C3, Cn. Traveling with speeds C1, C2, C3, Cn. C1, C2, C3, Cn. We can define the mean squared velocity. We can define the mean squared velocity. We can define the mean squared velocity and the root mean squared velocity and the root mean squared velocity and the root mean squared velocity as indicated below. As indicated below. Work. Right? Okay. Now We have proved so many equations now. The next equation which I'm going to write, the department has said don't prove it, just use it as it is. They have found out a relationship between pressure, volume, and this root mean squared or mean squared velocity. Pressure, volume, and mean squared velocity. This is the equation. You can directly use it. PV equals 1/3 mn c squared bar. P stands for pressure of the gas, you all know, no? Pressure of gas. V stands for volume of the gas. Volume of the gas. M stands for mass of a molecule. Mass of a molecule. N is number of molecules. N is number of molecules. C squared bar, all of you know, no? What do you call it? Mean squared velocity. Not root mean, na? What is it? Mean squared velocity. Clear? This equation we can directly use. This equation we can directly use in physics. Proof no need. Let's write. We can find the relationship between pressure, volume, and mean squared velocity as indicated below. Pressure, volume, and mean squared velocity as indicated below. Quickly write down. Okay. Right. Please look at the board now. Look, PV equals 1/3 mn c squared bar. Mass of one molecule multiplied by number of molecules. Mass of one molecule multiplied by number of molecules will give you mass of the gas. Will give you mass of the gas. A simple M is mass of one molecule. Number of molecules will give me mass of gas. I will mark it as M dash. M dash is mass of gas. I can't use the same symbol. No? PV. Also, you know, PV is equal to what? nRT. Then what can you say? nRT, wherever there is PV, I can put nRT. 1/3 M dash C squared bar. What is M dash? Mass of gas. Number of moles I can put mass of gas. Mass of gas is what? M dash. Here I have M dash mass. Divided by molar mass. RT. 1/3 M dash C squared bar. Simplify this. M dash cancel off. C squared bar cross multiply. 3RT over molar mass. That's mean squared velocity. You can find the root mean squared velocity by taking the square root. square root 3RT over molar mass. Looking at this, what can you say? 3 is a constant, R is a constant, molar mass is a constant for a gas. So for a gas, I can say root mean squared velocity proportional to absolute temperature. When temperature increases, root mean squared velocity will increase. Temperature reduces, root mean squared velocity will what? Reduce. Look and wait. Huh? I'll quickly prove and go. After the break, you can slowly write it. From here, we can go again. Look at this. PV equals 1/3 M N C squared bar. Here, M is mass of one molecule. Huh? I defined it correctly. Look at this carefully. Here we can say also PV equals NKT. Can remember? PV equals NKT. Wherever there is PV, I can substitute NKT. 1/3 MnC squared bar. N cancel off. Cross multiply. C squared bar is 3kT divided by mass of one molecule. If universal gas constant comes, what? Molar mass. If mass of one molecule comes, what? Boltzmann constant. From this, you can get the root mean squared velocity 3kT over mass of one molecule. Boltzmann constant is a constant. Mass of one molecule is a constant for a gas. Root mean squared for a gas, you can say root mean squared proportional to absolute temperature square. Okay. So if I prove it this way, here molar mass, huh? Capital M is molar mass. I think yeah, molar mass. Molar mass of gas. This is mass of one molecule. Mass of one molecule, here we have taken here. Mass of one molecule. Right. Look at this sum. PV equals 1/3 MnC squared bar. Mn is mass of gas, M dash. I have taken M dash here. This part here, M dash, mass of gas. Don't forget. I'll multiply by 2, divide by 2. What will I get? Mass of gas into mean squared velocity. What do you call this? Kinetic energy of the gas. No? Kinetic energy of the gas. PV. But all of you all know PV is equal to nRT. Here I can put nRT is 2 over 3 kinetic energy of the gas. Kinetic energy of the gas 3 over 2 nRT for n moles of gas. These are the ones in chemistry all are memorizing and dancing. 3 over 2 constant, n constant, r constant. What is your variable? Temperature. What can you say? You can say kinetic energy of the gas directly proportional to absolute temperature. Temperature increases, kinetic energy will what? Increase. Temperature reduces, kinetic energy will what? Reduce. Just one more adjustment. PV equals 1/3 MnC squared bar. Take M out, 2/3, sorry, take N out. Take N out, 2/3 half MC squared. 2n over 3. What is this? half mass of one molecule into velocity squared. Kinetic energy of a molecule. Earlier, kinetic energy of what? Whole gas. M dash is mass of gas. Mass of gas. Now kinetic energy of one molecule. Why? M is mass of one molecule, no? Mass of a molecule. PV. PV. But all of you all know PV is equal to NKT. Substitute here. NKT 2N over 3 kinetic energy of a molecule. You can find the kinetic energy of a gas. You can find the kinetic energy of one molecule. There you go to finish it off. Cross multiply. Kinetic energy of a molecule. 3 over 2 kT. K constant. 3 over 2 constant. Therefore, kinetic energy of a molecule directly proportional to absolute temperature. Done. Finished. Gas laws and kinetic theory of gases done. A break and come. After the break, you can slowly write. Write down the ones who need it. I think you did very end, except for uniform electric. Charged by induction. Then, okay. Quickly write. The problems we'll solve next week. These are the equations.